Today is April 17, 2024, about naive Bayesian algorithm. It's one type of classifier, probabilistic classifier, which means calculate probability and give outcome. So the core thing is we are giving the probability. That is the thing. What probability we are calculating? First, we started from probability function, which is probability CK, which is class and probability of observed sample. Condition is observed sample, and we are calculating for observed sample what probability is high. So each of the CK, find K is the bigger. This is the y hat. We are defining y hat by what is the biggest. Y hat is defined by maximizing the probability. That is why. So y hat is fundamentally maximizing probability. Okay. Then now this is the basic setup of naive Bayes. We will talk about then how it actually calculates the stuff. For first probabilistic classifier, we looked up logistic regression and linear regression. For logistic regression, they use fx equals to y equals to 1 or k or something. When a condition is x, then it will be 1 over 1 plus exponential minus b0 so on. This was logistic regression. So logistic regression was also probabilistic model, which is whether checking for whether y equals to 1 is bigger or y equals to 0 is bigger, and also finding the value that maximize y. So in naive Bayesian model, if you can see here, this is basically conditional probability exists. So we will review the Bayesian algorithm first. 99% sensitive means 99% true positive or real positive, and 99% specific mean 99% true negative or real negative. So it can be you can use this diagram you can use this table very easily, but basically yeah, there is every true value. It will be sample or prediction or our decision, whatever. So true first. We have seen this chart a lot. So our decision or whatever it is true, it will be positive, and it will be negative. And it will be first positive and first negative. First positive will be type 1 error, type error, and type 2 error. Let's say 0.5% of people are using drug. Then, yeah, if we use decision tree, it is way better to understand that intuitively. So there's 0.% of users who do drug, and not you will be non-users. Then probability of you is 0.5%. Then let's say drug test. We want to know if a randomly selected individual tests positive, what is the probability he or she is a user of drug? Then if we formulate this, what we want to know is when we did drug test, we want to know is when we did drug test, are they really using drug? This probability. But what we can know is when there are users use test, then let's say P, it will be 99% positive. If users do the test, probably it will be super high. Then we can get P plus intersection mu. There will be probability. But what we want to know is randomly selected individual test positive. What is the possibility he or she is a user of drug? This is the important question of Bayesian. Then what we should calculate is following. So we can calculate this by probability of u P plus bar u P plus. Then is equal with P u P plus u and if you use total law of probability, which is that will be sum of subset total prob law. If we use this one, then P plus will be P u P plus by u P plus by u plus P u bar P plus bar u bar. Yeah, then you can calculate the result, then it will be like 33.2%, which is super low compared to when drug users do drug tests and they will be positive. It's kind of different. When drug users do test and they become positive is when drug users do test, they become positive. What we want to know is if someone is positive, are they a drug user? Yeah, it's kind of different. So what we use is Bayesian, and now we'll go deeper to Bayesian classifier. So what we formulate is our needs is naive-Bayes classifier calculates following probability for every class, PCK. Then we use this. 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 Then we use this and for x, which is for this will be for observed sample x1 to xp. Then we can reformulate. We can use Bayesian theorem to reformulate this. We can reformulate this as probability of probability of x, probability of x. Then actually it is same with posterior equals to posterior equals to higher multiply likelihood. Evidence, which is unproved. Okay. Then we want to for samples, it's all same. So actually what we are maximizing is we can say px is same, so we can say we're maximizing this one, but we're now making it simply, we're simplifying this one, as we can now write it like this. Yeah, we are maximizing this one, and this is joint probability. If you want to calculate joint probability, it's kind of complex. I will give you an example why it is kind of complex. Let's see if there's are two random variables, then we should calculate basically mu and covariance matrix. Covariance matrix will be 2 by 2 matrix, and mu will be mu1 and mu2 because this is two random variables. Then in this case, what we should calculate is five parameters. But if we split it into two univariate variables, then they just have mu1 and mu2 and sigma1 and sigma2, which is there's no correlation term. This is 2 by 2 cases. But if you go to 3 by 3 cases, then parameter will exponentially increase in multivariate cases. But in univariate cases, it will just increase arithmetically 2, 2, 2. So that's kind of reason we will change it to more we will simplify it. We will simplify it. And now what we are going to do is simplify it. Okay, so we will, how are we gonna simplify it? We will before simplify it, if we just expand this, then it will be expand it here. This is same with a CK P X bar ck, and this is x1 to the xp. So we can rewrite this as p ck p x1 but ck, then rest of things will be px2 xp ck comma x1. This is the definition of random conditional probability. What we are using is definition of conditional probability. If we do this again and again and again, then we can get ck px1 by ck px2 multiplied by px2 ck x1 blah 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 blah. Then by chain rule, we will be able to write it as ck x psi ck. And yeah, now what we're gonna maximize is this one, y hat equals to r max this function. Yeah. Now what we're gonna maximize is this one. And in this case, important thing is C is same for every one. C is same for everyone. So first Bernoulli name setting, we will first the Bernoulli setting. So basically we are maximizing this one, but in Bernoulli setting, it will be probability or xct will be in Bernoulli setting, it will be in Bernoulli setting, it will be AKI xi minus AKI minus xi. Xi will be is a Boolean expressing the occurrence of event. And in Bernoulli distribution case, we know expected value of Bernoulli random variable is p, and variance is p multiply 1 minus p. Then what we can do is this probability distribution function. This is likelihood function. Then posterior, we can also get posterior, and we will calculate likelihood function, which will be equals to sigma j equals to 1 to probability of x3 but c yj equals to equals 1 to d oh my God. Then we can make it as log. And after that, we can find some point that is going to be 0. So we will feed this with, this is a lot of mathematics. We will feed it with simple graph again. So how Bernoulli knife Bayesian works is, let's say there's x and y. X is 1, 1, 1, 0. So 1, 1, 1, 0. 0, 0, 1. And y is 0, 0, 0, 0, 1. Then P, when y equals to 0, x equals to 0, x equals to, when P, x equals to 0, when y equals to 0, will be 1 over 4. And Px equals to 1, when y equals to 0 will be 3 over 4. And P when x equals to 0, when y equals to 1 will be 2 over 3. And Px equals to 1, when y equals to 1 will be 1 over 3. So equals to 0 when y equals to 1 over 3. P equals to 1 when y equals to 1 over 3. Then, yeah, we calculated probability. Then, based on this, yeah, you should remember these two together. How does it connect it? Understand. So result, if we make it as a code, then what code is actually doing is calculating this probability, and what they are giving is based on x, what gives the bigger? In this case, based on y equals 0, then it will give 1. And when it is 1, then it will give 0. And next is categorically based. In categorically based, the discrete random variables with more than 2 outcome cases. And we will also discuss it later. What we are going to see is naive, Bernoulli category, Gaussian and multinomial, and complement base. And if you see here, each of things, if we say there's m classes and n variables, then they will calculate m multiplied by n probability distribution. But in multinomial case and complement case, they will just calculate m probability distribution. We will also look through it later. And yeah, this is good example. This is Bernoulli distribution. It has two variables. Is it? Oh, two. I think it's two probability distribution, and which means there are two classes. I will figure it out. I will do a confirmation later, but basically I think there's two classes that I think I should see it as 4 variables. Then is it for probability distribution? I can't really understand it, but I will figure it out later. So in categorical variable cases, what we are doing is for Bernoulli cases and categorical cases, it will be probability of x can be, let's say, x1 to xn, then we will just multiply all the probability. So there can be m outcomes, and each of xj will be binary indicator, and pj will be probability of just outcome. So basically the probability distribution function will be pj to xj. And based on this, the thing that what we are gonna maximize will be sigma I equals to 1 to m, sigma j equals to 1 to m to p kj xj will be if we make a log, then it will be the ratio between n kj over n k. So we can also see it with categorical naive Bayes example. So that will be this time categorical x, y. It's because high category, so I need high row. High, low, high, high. And in this case, let's see, y is order. Then a probability of x equals to high when y equals to 0 will be 5 over 8, and other will be 1 over 8 and 2 over 8. And this is one probability distribution. And there's concept of parameter smoothing. Smoothing is concept related with parameter estimation, and it prevents zero probability when a category is not observed in a training data. Then it becomes problematic. So we usually use Laplace smoothing. So each of the numerator and denominator term, we add 1 alpha, and alpha usually be 1. And there's another multinomial naive Bayes, which is samples are represented as frequencies. It will be multinomial. It will be defined as p x. Pk will be pki x1. So in multinomial distribution case, then there will be maybe 3 binomials can be exist. We can use it, we usually use it when we check the words, that what word will come next. We can use it because in our dictionary, then there will be word and frequency. Maybe simply is 1 and great is 2, then we can figure it out if the writer is happy or not based on its frequency. So in multinomial, what we are going to maximize is y hat equals to ck, and it will be pki will be rough. Each of pki will be defined as xji plus alpha. This is Laplace smoothing tree, so I will just ignore it right now. So we cannot maximize it, or we usually do take a look for information, then we will maximize B plus W K transpose by X. And there's complement naive Bayes, which is this pki term is quite different with others, which is the frequency that xj is not, we usually find a frequent one, but we are searching for unfrequent one. And in Gaussian naive Bayes, what is changing is this part px plus ck, this part will be, when it becomes Gaussian, then we will use Gaussian function 1 over square root 2 pi sigma squared and minus 3 minus k squared over minus 2 sigma k squared. And so from these, we can also make some variations. And so if I organize what we did today, then there's probability distribution function, and we change it with simple format using conditional probability. Then we can represent it as prior function multiplied by likelihood over evidence, but we can ignore evidence because it's all the same. In this situation, we will find out k, what is maximizing, and then we will get, based on y hat, we can get this likelihood function, and it can be changed variously based on which naive we are using. And now we will see the code. First, what we used is Iris dataset, which has 3 classes, and each dataset has 50 samples. So in this case, we can see it's a class C. I have a question, what exactly happened when we change this part? Thing is, each of class, and we will do Gaussian naive Bayesian, and what they will give is mean of normal distribution from 3 different classes for different input variables. So each of the input variables mean you can see, and each of the variance you can see. And prior will be all same because we don't have any information. I'll just have same 0 and 1 and 2. And based on that, we can calculate each of mean of each columns. And we did Bernoulli distribution and log prior. Prior is just probability that we will get. And in another data set, we are checking columns, and this I guess we should use categorical distribution because for each of the column, it has different outcome with categorical values. So what we are using is categorical variables. I have an error here, so I will figure it out here. And I cannot match really this one and table and mathematical formula. So I'm gonna also figure it out later. And this time we are using multinomial. This is full code. Multinomial and complement base is what I also use. Thank you.